All right, so here's where we begin our discussion a little bit on what a system of equations is. On the previous page, on the previous part of this problem, we talked about the combination of cost for pounds of walnuts and raisins, and that they would need to add up to $15. And we talked about there's a number of possibilities of combinations that could work, all listed on the table. We had them on our graph as well. And so now we're going to add, though, another little constraint within the problem. The new piece of information is this. Diego bought a total of 2 pounds of raisins and walnuts combined. Write an equation to represent this new constraint. Like before, let x be pounds of raisins and y be pounds of walnuts. All right, so we still have the pounds of raisins and the pounds of walnuts as our constraints, all right? So as our variables, I should say. So x is pounds of raisins, y is pounds of walnuts. But instead of talking about money on this particular part of the constraint here, we're talking about pounds as a constraint. So in this case, 2 pounds of raisins and walnuts combined is the constraint. So let's just think about that. That means that if we have the pounds of raisins and we add it together with the pounds of walnuts, that will total 2. All right, so this is not a money equation. This is just a straight adding up the pounds of raisins and walnuts that they have to add up to 2. All right, we still need to, though, be true to our previous constraint, which was about money. So this one was about money from our previous page, and this one is about just straight up pounds, okay, total. And we need them to all work together, all right? We need those two equations to work together so we have a combination that works for both the total pounds of 2 and the total amount of money of 15. Use Desmos to graph both the equation from number 1 and the 4x plus 8y equals 15 equation from the previous page on the same axes. Sketch or paste the graph below. All right, so if you still have the one on the previous page, then that should probably work out pretty nicely. Let's go back over to Desmos, and then let's put that in there. So if we click on little box below the previous equation, we can add another equation, and that one was x plus y equals 2. All right, so notice you get a different line, and same variables though. We still have raisins on our x-axis and walnuts on our y-axis. So let's go ahead and screenshot this. I might also highlight that point right there. I'm just going to screenshot, so I'm just clicking on that point of intersection because we're going to come back to that. Maybe you can do some prediction about what that point, how that point will be important for us. Oops, I forgot to get in there faster and go ahead and edit it. So let's see if we have that here. All right, here we go. And I'm gonna crop this a little bit, I think. Okay, looks good. All right, let's bring that in. Okay, there we have both equations now are graphed. The blue one that you see is the original one, the 4x plus 8y equals 15. The black one is our x plus y equals 2 equation. Right, complete the table with the amount of one ingredient Diego could have bought given the other. Be prepared to explain. All right, so pounds raisins and pounds walnuts. Remember, our equation was x plus y equals 2. All right, this one's maybe an easy one to fill in the values because all the x and the y values have to add up to 2. Notice 0.25 plus 1.75 has to add up to 2. All right, and so that one, that's the one they actually see on the graph. And notice these add up to 2, these add up to 2. So all the combinations have to add up to 2 for this part, and this is on our black line. So actually I'm going to coordinate here. I'm going to use black to color over that. So if we think about that, so if we have 0 pounds of raisins, then of course we're going to need 2 pounds of walnuts for that to work, right? So 0, 2 would be that one. And if I have 1.25 pounds of walnuts, so if walnuts is 1.25 and it has to add up to 2, that must mean this is 0.75 plus 1.25 adds up to 2, right? You could do these in your head. I mean, if you want to just solve it algebraically, do a little solving here, yeah, we would subtract 1.25 from both sides of the equation, and x is equal then to 0.75. But in this case, you could probably do a lot of these in your head. What about the one down here? If we have 3 pounds of raisins, right here, right? If we have 3 pounds of raisins, 3 plus y equals 2. Oh, wait a second here. How could 3 plus y equal 2? Well, if we are thinking about that, that really means that y would have to be -1. 3 plus -1 would be equal to 2, which on our table is a combination that works. But if we think about our constraints, this right here doesn't really make sense. So that would mean we would have a negative pounds of walnuts. So it doesn't make sense in the situation to have negative pounds of walnuts. All right, so this is where we have to use our brains a little bit, right? Because mathematically that works. 3 plus -1 is 2. But in the problem, in the context of our problem, it only makes sense to have positive values for pounds of raisins and positive values for pounds of walnuts. And that's why I was saying earlier, I was really focusing in on our x-axis, which we know is our raisins being positive values, and our y-axis, which is walnuts in terms of pounds, being positive values as well. So that's why we kind of zoomed in on that first quadrant where we have positive values for both. Okay. So if both pieces are brought together then, so if Diego spent that $15 total, and then he also bought exactly 2 pounds of raisins and walnuts total, how many pounds would he have to buy? Well, it has to work then in both of the equations, because this table works for the pounds, and our previous table works for the amount of money, but we need it to work for both. And not all the combinations work for both, right? Because if we take, for instance, this point right here, this works for our raisins and walnuts pounds, but it doesn't fall on the money. Remember, this is our money one, and this is our pounds line. Okay, so it works for the pounds, but it doesn't work for the money. Right? And if we took, for instance, this point right here, okay, this works for the money line because it's a point that is on the money line, but it's not on the pounds line, so it doesn't work for that. So question is, what works for both of them together? And some of you guys may have already been thinking about this and seen this. Where it works for both of them together is right there. That point works for both money, the money equation, and the pounds equation. It's the only point that works for both because it's on both of the lines. So what is that point? Well, I highlighted it earlier, 0.25, 1.75, and we know that is the solution that works for both of them because we see it in both tables as well. 0.25, 1.75 is in this table for the pounds, and 0.25, 1.75 is in this table for the money related problem. And none of the rest of the points that are in the tables are in both tables together. Like, for instance, 0, 1.875 here, and the other one has 0, 2. So that's different. So the one that works for both of them, we should be able to see in both tables, and we can see that on the graph as well where the lines cross. All right, so let's write that down. 0.25 pounds of raisins and 1.75 pounds of walnuts works in both equations. I'm going to say the money equation and the total pounds equation. We see it as the intersection of the lines on the graph and the same values that show up in both tables. Got a little wordy there, but you can condense that into your own words if you want. But the key is to see it in both places. It works in both. We see it as the intersection point on the graph because it works for both lines, so it's on both lines. And we see it as the values that show up in both of the tables. Congratulations, you have just solved your first system of equations of the year using a graph and a table, and the system meaning that we have more than one equation. We have two equations that we need to solve simultaneously together at the same time and find an x and a y value or a combination of values that works on both of them.